Hi, friends. I'm super excited to tell you all about my latest favorite passion, Quebec's power grid, because it's surprisingly indestructible. But it wasn't always that way. So I want to start with a story, or rather three stories, of times that this massive system has failed. So when Quebec originally designed their power grid, they knew that it was a snowy province, and they knew that they'd have ice storms. So they engineered it so that every exposed surface could withstand an inch or so, 1.2 inches of ice buildup everywhere. So that means every wire, every pylon, everything could be coated in a full inch of ice buildup before their system would fail. Of course, that didn't last so long. So in 1961, they had an ice storm that knocked everything out, and then they upped the rating to 1.8 inches. And then, of course, in 1986, it happened yet again, knocked the whole system out, and they upped the rating again. So finally, they got fed up of everything getting knocked down, and they built it to withstand, I believe, 1.8 inches, which was way higher than anything else in the world, for context. Even Alaska or Siberia didn't have ratings this high, in particular because Quebec's snowfall in certain areas is very high. And then, of course, in 1998, the big one happened, the famous ice storm that knocked out the entire power grid yet again. And it was due to 2.8 inches of solid ice buildup on every exposed surface. 17,000 plus power poles had to be replaced, thousands of kilometers of lines, and of course, millions of people didn't have power. And it was so bad that they had to send electrical repair crews from North Carolina and South Carolina up to Quebec to help fix the system. And it took weeks for them to rebuild, and they learned a lot of lessons since then. So for context, in Quebec, all of the power comes from a small region in the northwest area of Quebec in the James Bay. And it's called the James Bay Project. And they set up several dams in the 1970s and then long distance transmission lines from those dams to cities. And the reason why this is interesting is because Quebec was the first country or region ever to do really long distance high voltage transmission lines. So Quebec pioneered the first 735 kilovolt lines. And at the time, the highest lines in the world were at 300 kilovolts. So they over doubled the voltage rating so that they could get really, really long distances at high efficiency. And Quebec today runs on over 90% hydroelectric power, and mostly from those dams. And the power goes all the way down from those dams into the cities and even down to New York City. They sell a lot of power into the US. So a quick overview of the James Bay Project. It's incredible. It's the largest hydroelectric installation in the world at 27 gigawatts of maximum capacity. It's huge. And it won out against proposals for nuclear power back in the 1970s. Unfortunately, it had a huge cost. So they had to flood almost 13,000 kilometers of land, 11.5 thousand kilometers of which was owned by Cree and Inuit native populations. So they gave those native populations 250 million in exchange for that land. And in the process created the largest body of water ever made by humankind and is now the largest freshwater lake in Canada. So it's as I mentioned, it's all those mega dams near the Arctic Circle that are holding back this flooded area and then slowly releasing it over time to generate hydroelectric power. And of course, because Quebec is separatist at its core, it's an entirely separate grid from the rest of North America. North America has 5 grid regions, and Texas and Quebec are both independent, separate from the rest of the major grid regions. This is what it looks like in the summer. This is called the Giant's Causeway because these huge steps are the spillway for the dam. And then this is what it looks like in winter most of the year. I'm sorry I couldn't find higher resolution photos that were public free to use. So how do power grids work? It turns out coming out of your wall, you have single phase AC. So in the US, that's 110 volts, and it looks like a sine wave. So if you plug in a voltage or an oscilloscope into the wall, you'll see one nice clean sine wave at 60 hertz. So 60 times per second it's going above, and 60 times per second it's going below 0 volts. And the reason why we use AC is because Tesla won, if you like the Tesla and Edison wars. It turns out that AC is easier to convert between high voltage and low voltage than DC. And that's because transformers rely on AC because you need a change in electric field for a transformer to work. So old school power grids ran entirely on transformers and fuses or breakers. and regions would be connected, and you'd have big long distance wires at very high voltage, and then local wires at lower voltage with transformers going between the two. Modern systems are a lot more advanced than that. We have capacitors, we have thyristors, we have optic coupling of like digital control systems, because when you have such high voltages, you can't just like plug an Arduino into a relay and turn them on and off, right? It'll fry the whole thing. So you have to use fiber optics to couple the signals for the control circuitry so that you don't accidentally zap whatever it is that's deciding when to turn power on and off. The other major issue that power grids deal with is a changing load. So over time, throughout the day, throughout the month, throughout the year, the load on the electrical grid varies wildly. And a lot of the job of electrical operators is to respond to those changes in load quickly, and also respond to the economy of how power is sold and bought. So when power is cheap in a certain region, it makes sense to ship it over a very long distance to a more expensive region. But other times it may not make sense to do that. So a lot of the job of people who operate power plants and power grids is balancing the frequencies and the phases of the power system to make sure that it all stays operative and that we're not lagging. And what I mean by frequency synchronization is that when you think of a power grid, think of big spinning wheels, big flywheels inside of power generating plants that are really heavy. And that spinning kinetic energy is actually one of the major safety systems in a power grid. So if the power were to go out, or if a sudden spike were to happen where a lot of load is placed on the system at once, all together in sync, all of the power grids and all of the power generation plants in that region will start spinning slower because you're pulling energy, kinetic energy, out of the wheels and turning it into electrical energy. So managing that kinetic energy and making sure that the wheels all stay spinning at the same rate and all together in sync is super important, and it's one of the hardest things. And to make it even more complicated, measuring the system is very, very different than measuring some microelectronics. So they use tools like, I'm blanking on the name, but there's one tool in particular that's really cool where you can bounce a signal off of the end of a transmission wire and watch it come back and measure how long the transmission wire is and if there are any faults in between, because any change in impedance in the wire will cause a reflection in signal. In the same way that waves bounce off the end of a pool, signals bounce off the end of a wire. So they'll often send signals down wires to see where did the wire go down. And it's like, oh, at kilometer 236. And then they send out a car or a helicopter and they replace that one part. Another major issue is that the whole grid is actually a giant antenna. So any signals that you put over the wires end up radiating out into space. And I'll get back to that a little bit later. So we talked about AC. We have three-phase AC powering most of the system. And that's because Tesla won the current wars. But DC is making a comeback. So these days, high voltage DC is a big part of modern power systems. So Edison is actually coming back from the grave a bit because it turns out that DC has a lot of advantages over AC in different applications. So DC wiring is actually more efficient than AC wiring because there's no skin effect pushing the electrons to the outer surface of the wire. You can actually use the whole wire, including the core, to send electrons. So you don't need as much physical steel to run the cables as you do AC. It's also fewer conductors. It's only 2 wires, positive and negative, versus AC, where you have 3 phases and then often a return wire. It's also much easier to control digitally. So there's something called static varocompensation, where you have a very high amount of DC current available, and you have your normal AC system that's going to the rest of the grid. And then if any problems happen with the AC signal, like let's say it starts to lag, or there's not enough current to supply the grid, you inject DC current at exactly the right time in the phase, and you can boost and repair AC grids that are failing using DC current and some control circuitry, and that's much easier to do with DC than AC. So I touched on that a little bit, but one of the biggest positives of DC is that it's a rescue lifeline for other grids. So connecting Quebec and New York is actually a single high voltage DC line, the longest in the world, going straight from the James Bay Project Dam all the way down to New York City. And off of that line are little interconnects to local grids. And if ever one of those grids accidentally shuts down or loses power, they use the DC line because it's not in sync with the rest of the grid. Remember, all the grids have to be in sync together. Positive, negative, 60 times per second together. But DC doesn't switch. So when they have that DC line coming down, they can use the DC to restart all the spinning turbines and generators in a power plant that need energy to start when the rest of the grid has gone black. So when you have a full blackout, like if anyone remembers the New York blackout of a few years ago, you actually need power to restart the system. You can't turn on a power plant unless you have power to bootstrap it. And this is something we see in software as well. Sometimes you can't start the database server until the auth server is started. But what if the auth server relies on the database server for some of its functionality? You end up with circular dependencies. So one of the major benefits of high voltage DC is that it helps you break those circular dependencies by introducing an extra source of power that you can use to restart systems that have gone down. And the last thing is super cool, I think. Quebec, I think, is one of the only places in the world that does this, but they'll actually short circuit the power lines and run high voltage DC on them for 30 minutes to melt all of the ice off of the wires. So they'll send thousands and thousands of megawatts down super long distance wires over thousands of kilometers, and they'll literally just get them hot until the ice melts off, and then they reconnect them back to the rest of the grid, and business continues as usual. That's a very unique feature of Quebec's power system, is this de-icing based on high voltage DC. So the question that you all came here to have answered, can the power lines run TCP? It turns out yes, and people tried to do this for a long time. And actually today, there's a lot of signals running over power lines still. So at different frequency ranges, there are different signals, and they're coupled onto the power lines using capacitors. So just like with radio in the atmosphere, you couple signals with capacitors because capacitors help you filter certain frequencies above a certain range or below a certain range. So on our power lines in your house and around the city, there are a bunch of different frequency bands. The lower frequency bands tend to be used for home automation or reading meters or small, like low bandwidth things. And then around the 1 megahertz range is where you start getting Ethernet over power. So you have wall adapters that plug into your wall outlet in your house, and you can send Ethernet over your power lines in your house to somewhere else in your house. But of course, that signal degrades with distance because of capacitive coupling between lines. So that Ethernet signal bouncing around in your house's power lines probably doesn't make it to your neighbor's house because maybe there's a transformer or something else that it has to go through. So that's a bunch of signals. And then the real question is, can we send internet over really long distances with broadband? And yes, they tried to do this. This was called BPL, long distance broadband backhaul over long distance power lines. And the issue, the reason why we don't actually see this happening today is because it turns out astronomers get really, really mad. The whole power grid is a massive antenna. And when you send megahertz or gigahertz signals on this massive antenna, you completely drown out everything else in noise because it's the largest, most effective antenna there is. So today, we actually don't run internet over power lines over long distances because of the interference issues with all the other systems in the world. And it turns out that it's quite difficult. You get losses, and fiber is easier in the long run. So this is what like a long distance broadband over power line setup looks like. You would inject it and then pull it off the lines close to the house. And every time there's a transformer, you have to extract it and then re-inject it on the other side of the transformer, because transformers aren't good at coupling frequencies that aren't the frequencies that they're designed for. So what does this have to do with software? Just to wrap this up, there are a lot of lessons that we can learn from large grids and how they engineer around failure and dealing with failure. So grids are designed as modular systems. All the interconnects between grids are standardized internationally. There are common pieces that are plugged in and used all over the place. The frequencies are standardized. There are 5 grid regions in North America, and there are others in Europe, and they all communicate with each other in relatively standardized ways, save for a few regions that are special cases. It's a distributed system in the true sense of the word. You have all the same issues as you do with software distributed systems. You have time synchronization issues. You have to elect leaders to decide who comes back online. And you have to be able to apply back pressure. So when there's a lot of load in a system, you have to somehow respond back to that load and tell people, hey, stop using so much power. Or tell the power plant that's generating, hey, you need to actually generate more power to come up with this. So in all the same ways that we deal with this in software, they have to deal with this in hardware in a critical system. So that's the other major thing, is the power grid is a very critical system. It's relied on for millions of people's safety. It's used in hospitals to keep people alive. It's used all over the place. And it needs to be able to degrade gracefully. So when faults happen, they have lots of systems in place that allow them to gradually reduce load or segment different parts of the grid individually such that they don't take down the whole system. So South Africa over the last year has had a lot of issues where they do what's called load shedding, where they'll brown out whole regions or they'll black out whole regions in order to save the overall health of the power grid. That's one way to do it. Another thing that has to be dealt with is split brain situations. So if two power grids go down and then they restart independently, they may be spinning at different frequencies or different rates. And when they resync, they have to actually physically slow down the generators until they're in sync again and then reconnect them together. And you get huge sparks when you close these breakers. It's pretty cool to watch online. And then the last thing is it's a human system. Fundamentally, like any complex software system, it's humans at the end of the day. So Hydro-Quebec in Canada is a 22,000 person company. So like Google, they have similar issues internally where they, even just to communicate the specs of what do we do in case of a failure, how do we sell power to other people? What happens, if they don't want to sell power back to us at the same price that we sold it to them? There's all sorts of politics and things that need to be dealt with. And as a closing note, I want to touch on one of the best solutions that Quebec has had for dealing with massive distributed failures, and that is designing everything in circles. So the power for Montreal arrives to Montreal from a circle. There's a ring of pylons that form a circle around Montreal, and all the power that comes to Montreal goes to the circle. And this is cool because if there's a break at any point in the circle, the power just takes the long way around. And this design is what saved Montreal from many more blackouts and power outages over the last couple of decades. And I think more systems should take inspiration from this, of dealing with a ring of providers such that if any position in the ring is broken, you can share data around the long way around and the whole system doesn't go down. So that's it. Thank you so much. The conference has gone super smooth. Thank you, organizers, AV team especially. And yeah, if I got anything wrong or if you want to point stuff out, just talk to me on Twitter or Discord.